In this video, I'm going to talk about quantum numbers and electron configurations. Some of this video is a review, so I might move through it a little bit quicker, and then some of it is new, and we'll kind of take our time through that and make sure we're good with this for AP. So again, here we have seen some of this before with just a little bit of new. So we know that there are four numbers that represent the address of an electron. We have four quantum numbers that represent the address of an electron. And we only really focused on two of them in honors, and we might have mentioned the other two very quickly, but you only were responsible for dealing with the first two. But now we're going to look at all of them. All right, so we have NL, ML, and MS. So just a little reminder here. Electrons are negatively charged, the nucleus is positive, so the electrons are attracted to the nucleus, but those electrons are repulsed by other electrons. I know that's kind of something you probably know, but just, remind yourself about that. So our goal here as we move through this is going to be to talk about the four quantum numbers and then be able to actually determine or identify the four quantum numbers for each particular electron. And actually, it's something that's usually kids really like, and it's actually easier probably than you think. The first quantum number here we know is called the principal quantum number. We use N to denote this. This is your energy level on the periodic table. So it's the areas around the nucleus where you're likely to find electrons, and it tells you how close the electrons are to the nucleus. So it goes from 1 to 7. 1 is lowest in energy, closest to the nucleus, and then as you work your way out, you get higher numbers here. So principal quantum number is the energy level. Remember, the closer these electrons are to the nucleus, they are lower in energy, but they penetrate the nucleus more. All right, so just be careful with that. Remember, if you were talking about this in terms of PES, those electrons that are closer would take more energy to eject them, but in terms of the overall energy of the electrons and the energy level, they are lower in energy if they're closer to the nucleus, but they do penetrate the nucleus more and feel the full nuclear charge here and full effects of the nucleus. As we said, lower in energy, ground state would be when your energy level is 1, and then the excited states are anything higher than that. And obviously, electrons that are in higher energy levels here are going to have bigger paths, bigger orbits around the nucleus. Obviously, we know that it's not perfect. The Bohr model is not a perfect representation of the atom, but it definitely helps us understand where these electrons are located. And electrons that are more excited states have larger paths around the nucleus, so therefore they have more energy. Remember, if you're trying to figure out the maximum number of electrons in any energy level, just do 2n squared, where n is your energy level. All right, that'll tell you the maximum number of electrons for any energy level. So the principal quantum number can be found on the periodic table. The rows on your periodic table typically indicate your energy level and tell you about the principal quantum number. So depending on which row you're in, all right, that's going to be basically your principal quantum number. But remember, your D sublevel here, they're always one row or one energy level off. So if you look at your periodic table, it goes from 1, which would be closest to the nucleus, lowest in energy, all the way up through 7. All right, so you definitely need to be able to identify the principal quantum number here by looking at your table. The second quantum number that we need to know about is the azimuthal quantum number, and we use L to denote the azimuthal quantum number. This is representing the shape of the orbital. Remember, we have these energy levels, which are areas outside the nucleus where electrons can be found, and they can be kind of split up into these sublevels or subshells. All right, so we're just kind of now going inside an energy level. All right, so inside an energy level, there are these sublevels. Again, just areas where you're likely to find electrons. And the sublevels we know are S, P, D, and F, and you do increase energy as you go from S to P to D to F. All right, so S's would be lower in energy. Remember, the S electrons penetrate the nucleus more. all right? So they're attracted to that nucleus more, therefore they are experiencing lower energy. It would take more energy to eject them, all right? But because they are attracted to the nucleus and they are penetrating the nucleus more, they have less energy here. So anytime you're trying to figure out azimuthal quantum number, you want to think about, okay, what sublevel am I in, SP, D, or F, because that'll give you information about the azimuthal quantum number. All right. You do need to know the information here. You need to know that S's have an L value equal to 0. They can have 2 electrons at the most, and they have a spherical shape. All right. You should know what it kind of looks like, but usually you don't have to draw these or anything like that, but you should definitely be aware of the shape. We know that all that happens here is you go from S to P to D to F. Your L values just go up by 1. So if you were in a P sublevel, your azimuthal quantum number would be 1. P's hold 6. They're a dumbbell shape. D's have an L value or an azimuthal quantum number of 2. They can hold 10 electrons at the most. They have a shape of a double dumbbell. And F's have an L value of 3, 14 electrons at the most, and we don't care about the shape. So anytime you're asked about the azimuthal quantum number or you're trying to figure out the azimuthal quantum number, you need to pay attention to what sublevel you're dealing with. And you need to know that S starts an L value of 0 and it just increases by 1 as you go from S to P to D to F. Don't forget the sublevels are visible on your table as well, so you kind of need to know where those are at. The S's are the far left 2 columns here on the periodic table, including helium. Your P's, all right, are over here on the right. The D block is in the middle, and the F's are at the bottom. So again, this should be a review, but just realize those sublevels are there on your table, and knowing what sublevel you're in, you could figure out a particular azimuthal quantum number. So the principal quantum number and the azimuthal quantum number should be a review, but you do have to use your table, your energy level, and your sublevel to figure those out. So now we're going to talk about the magnetic quantum number, or the third quantum number here. We use ML to denote this. This is basically talking about the orientation of an orbital. Basically, these are areas in a sublevel that can hold a maximum of 2 electrons. So we talked about energy levels, which are just areas outside the nucleus where you're likely to find electrons. Sublevels are areas inside the energy level. And now the magnetic quantum number is referring to orbitals here, and these are specific areas inside a sublevel that can hold a maximum of 2 electrons. Remember, these electrons are spinning oppositely. If you remember how they would look in an orbital diagram, you draw one going up, one going down. But now we need to worry about the values here of the magnetic quantum number. These values range from -3 to +3. So the only possible values you could have for this quantum number are -3 all the way up through +3, including 0. All right, so basically what we say is it could go anywhere from -L to +L, including 0. Remember, the highest possible value you can have for L for an azimuthal quantum number is 3 for your F. So you can only go from -3 to +3, or -L through +L. Remember, every sublevel has a different number of orbitals. All right, each orbital can only hold at most 2 electrons. So this corresponds to how many particular electrons a sublevel can have. S's only have 1 orbital. Remember, orbitals are the boxes if you were doing orbital diagrams. So you would only ever draw 1 box or 1 orbital for an S with at most 2 electrons in there. P's have 3 orbitals and can hold 6 electrons. D's have 5 orbitals, can hold 10 electrons. Remember, 2 electrons in each orbital. And F's have 7 orbitals, which can hold 14 electrons. All right, just remember, take the number of orbitals times by 2 because each orbital can only hold 2 electrons. So we got to look at this magnetic quantum number obviously a little bit more, but just realize the values of this can only be from -3 up to +3, including 0 here. In order to do the magnetic quantum number, you need to look at which sublevel you're in. All right. So the easiest way to do this is if you were drawing an orbital diagram, all right, you put 0 as the middle box for the particular orbital of the sublevel you're in, and then you just kind of go outward here in both directions, -L through +L. So for example, if you have an S, all right, the L value here of an S is always L equals 0. So your only possible values here for the magnetic quantum number for an S sublevel would be 0. All right, and it makes sense. There's only one orbital for an S, so you would label an S orbital here 0. But then P's get, where you have a little bit more interesting. The L value for a P is equal to 1. All right, and I know that looks the same, so let's just make it look like a 1. So that means the P sublevels can have anywhere, for their ML values, can go from anywhere from -1 up to +1. All right, so what you do is you always have 3 orbitals for a P. So your middle P box, you label 0, and then you put -1 to the left of it, +1 to the right of it. So basically what that means is if you had electrons in this particular orbital for that P sublevel, they would have ML values of -1. Any electrons in this particular orbital would have ML values of 0, and so on. But it's the same idea here. D's have an L value of 2. So for the D orbital, you can have ML values of -L to +L. So -2 to +2. In your middle orbital, you always put 0. And then just, the negatives go on the left, the positives go on the right. So -2 to +2. And then the same thing for F. F's have an L value of 3. So you can go from -3 to +3, put the 0 in your middle orbital, and then number in both directions. So that's basically how you would figure out the third quantum number, the magnetic quantum number here. And it does depend on which sublevel you're in and which numbers it's going to have. But it goes from -L to +L, including 0. The fourth and final quantum number is relating to the spin, and we denote this as ms. Basically, this is the quantum number that distinguishes the electrons in a particular orbital. So if you remember, the electrons always spin opposite. One's going up and one's going down. So we give them possible values here of +1/2 or -1/2. All right, that's indicating that these electrons have opposite spins, and we do show them as having opposite spins when we draw the orbital diagrams. So typically, the electrons that are going up are the +1/2, and the electrons that are going down are the -1/2. Remember, these quantum numbers are giving you the address of a particular electron. So they have to have a set of 4 different quantum numbers for every electron. So the first 3 quantum numbers for electrons could be the same. It's just that this last quantum number is differentiating the 2 electrons. And we'll see that as we start assigning quantum numbers here to electrons. Just a little review here of the quantum numbers. The first quantum number was the principal quantum number. We use N to denote that. It's talking about the distance from the nucleus. It's your energy levels on your periodic table. The second quantum number is your azimuthal quantum number, L. It's talking about the shape here. We use the sublevels to figure out the azimuthal quantum number. The third quantum number is the magnetic quantum number. It basically uses the sublevels as well. It's talking about a specific orbital in the sublevels. It can go anywhere from -L to +L for values, including 0. And then the very last quantum number is the spin, and it can have values of +1/2 or -1/2. So when we're assigning quantum numbers here for electrons, we will have the principal quantum number first, then the azimuthal, then the magnetic, and then lastly the spin. And you'll see how this will give us a set of 4 different quantum numbers for each electron. This slide just summarizes pretty much all that information about energy levels, sublevels, orbitals, and the maximum number of electrons you can have. All right. Remember, your energy levels here are your rows on the periodic table. You could look at your table and see which sublevels are in which energy level. For example, in energy level 2, you only have a 2s and a 2p. That's why there's only 2 sublevels there. To figure out the number of orbitals for any energy level, you just do n squared. So if you're in the second energy level, 2 squared is 4. You have 4 orbitals, but it also makes sense. Think about how many orbitals you would draw for each of your sublevels. S has 1 orbital. P's have 3 orbitals, so 1 plus 3 is your 4. But you can use n squared to figure out the number of orbitals for any energy level. And then remember, the maximum number of electrons for any particular energy level is 2n squared. So this just basically summarizes that information from the table. Remember, we use all this information to do electron configurations. So this is a review. Remember, there's orbital diagrams, which uses the boxes and the arrows, SPDF notation, which is a shorter version of that, and you have kernel notation, which is even shorter, which uses the noble gases here. So you do need to be able to do all of these electron configurations, but again, that's a review, that's nothing new. Don't forget the rules we use here for the electron configurations. You still need to know these. The off-bow principle is basically saying we add electrons one at a time to the lowest energy first. That's why we do 1s and then 2s and then 2p and so on. Pauli exclusion basically says the electrons must have opposite spins. You only have 2 electrons per orbital with opposite spins, and basically this gives us a set of 4 different quantum numbers for each electron. And then Hund's rule says that basically you have to have 1 electron in each orbital before you would ever pair them up. So if you had 3 electrons in a particular sublevel here, you would put 1 electron in each of the orbitals, and then when you added the 4th or the 5th, that's when you would start the pairing. So these are not anything new. Definitely still need to know these. You can reference this if you need to, but it's just going through the steps here about how to do orbital diagrams. Remember, these are the ones with the boxes and the arrows. You have to follow all your rules, but we've done this inside and out before in honors, so I'm not going to go through all the steps, but definitely something you could review and go back and even look at some older videos if you need to. This is just showing you the specific energy level, sublevel here for each of the different elements on your table. And remember, when you're doing this for orbital diagrams, you always start at the lowest energy level. You always start with the 1s. You essentially always start with hydrogen. And then you just keep tracing, following the atomic number as you go until you get to the element where you need to stop. So the beautiful part of this is that you just use your table to do the electron configurations. Okay, so this would be something new here, where you're trying to assign quantum numbers to every electron here for a particular element. So the first thing this said was draw the orbital diagram for oxygen. So if you don't remember how to do orbital diagrams, definitely review that. But this would be the orbital diagram here for oxygen. 1s2, 2s2, 2p4, and you can see the arrows representing the electrons here, but the last part is new. It says assign 4 quantum numbers to each electron here. So every one of these arrows represents an electron, so every one of those arrows needs a set of 4 quantum numbers, and no 2 electrons should have the same 4 quantum numbers here. Okay, so if we look here at the first electrons, I find it easier always just to start with the first electrons that you're putting in the 1s. If you remember here, the first number you write in the address of the electron for the quantum number is going to be your energy level, your principal quantum number. The second number is going to be based on the azimuthal quantum number, which is based on the sublevel. The third number is going to be the ML, the magnetic quantum number, based on the L value here and your particular orbitals. And then the last quantum number is either going to be plus 1/2 if the arrow is going up or negative 1/2 if the arrow is going down. All right. So if you are looking at this electron right here, all right, so the first quantum number is going to be based on the energy level. Well, if you notice, that's the big number here. So you immediately know that this electron, the first quantum number, is going to be 1. Okay. The second quantum number is the azimuthal quantum number. Well, that's based on your sublevel. If you're in the S, you have to say to yourself, okay, what's the L value of S? Well, when L equals 0, that's an S. So the second quantum number is going to be 0. because you're in an S. The third quantum number, remember, is based on the ML. And if you remember here, it always goes from negative L to positive L, including 0. So if you label your box here, all right, for an S, the ML is always just going to be 0, all right, because that's the only value you can have for an S. So if you do this for all of them right now, S's would have an ML value here of 0. And then when you get to a P, you can go anywhere from negative L to positive L. Well, P's have an L value of 1. So you can go anywhere from negative 1 to positive 1. But remember, if you just put the 0 for the middle orbital, and then you know that to the left of it's going to be negative numbers, and to the right of it is going to be positive numbers, you know that this one would be negative 1, and this one would be positive 1. So you don't even need to really be too worried about the negative L through positive L. It just kind of works doing it that way. All right, so if we look at this for this first electron here, the ML value is just going to be 0. And then because the electron is going up, it's plus 1/2. So the second electron here in the 1s is pretty easy because the first three numbers are going to match and be exactly the same. It's the last number that's going to be different. This is in the first energy level, principal quantum number of 1. It's in the S, so it has an L value of 0. It has an ML value of 0 as well, but because it's going down, it's negative 1/2. So if you notice, the quantum numbers here, the set of quantum numbers for each of those electrons is different. They are not exactly the same. They are very close. For the first three, they match, but the last number is what makes them different. But then you could do this for all the electrons here for any particular orbital diagram. So now if you move on to the 2s electrons, same deal. Both of these, you're in the 2, the second energy level. So the first quantum number, the principal quantum number is 2 for each. You're in the S again. So the azimuthal quantum number, the second one here is 0 for both. And because the ML for every S is 0, they both have a third quantum number here, the magnetic quantum number of 0. And then again, the difference is plus 1/2 for the one going up, minus 1/2 for the electron going down. All right, so now we're going to be in the electrons here for the 2p, and this is where it gets a little bit more interesting, but basically it still follows those exact same ideas. We're still in the second energy level. You can see here it's the 2p. So the first quantum number for all the electrons here is going to be 2. We're in the p though, so the azimuthal quantum number now increases to 1. P's have an L value equal to 1. So the second quantum number for all the electrons here is going to be 1. And then depending on which orbital they're in, the ML value can be -1, 0, or +1. So these electrons that are here in the first orbital here in the P that's drawn, they have an ML value of -1. So notice both of these have 2, 1, -1 as their first three. And then the difference here, the one going up is +1/2, the one going down is -1/2. So this set of quantum numbers here would represent this electron. And then for the last two electrons here, again, the first two quantum numbers are going to be the same. And then it's the last two that you got to kind of worry about here. This one that's in the middle, well, that's going to have an ML value of 0 because the middle box, the middle orbital is always labeled as 0. It's going up, so it's +1/2. And this last one is in the last orbital here with an ML value of 1, but it's going up, so it's +1/2. So if you notice, the 4 quantum numbers for every electron are different. They do not match any other electron, and that's what we should be seeing here. So you could do this for any orbital diagram, any element. You just have to pay attention to the 4 different quantum numbers. All right, so now we're going to try this example here. It wants you to draw the orbital diagram for aluminum and then assign the 4 quantum numbers to each electron here. Sometimes when you're given one of these problems, it might just ask you to assign quantum numbers to maybe the valence electrons or something like that. But for this example, it does want quantum numbers for each electron. So what I would do is I would pause the video, try this on your own, and then when you rejoin, you'll see the entire answer so you can see how you did. Like I said, usually people like this, and it's usually pretty easy because you're just taking all that information you learned and you finally put it all together here from honors. So definitely pause the video, try this one, and then rejoin to see how you did. Okay, so hopefully this is the orbital diagram and the quantum numbers you got for aluminum here. So you definitely need to be able to do the orbital diagram, and then you definitely need to be able to list and show the quantum numbers for each of the particular electrons. All right, so just pay close attention to which quantum number you're dealing with, which energy level, sublevel you're doing, and you don't have to write the numbers here for the orbitals, but I find it easier so that I can quickly do the ML values. Just remember that if an electron is going up, that's typically going to be your positive 1/2. So now you should be able to do an orbital diagram and determine the 4 quantum numbers for any electron here. Some new terms here for AP that we need to be concerned about: paramagnetic and diamagnetic. So if something is paramagnetic, that would be when it is attracted to a magnetic field because it has one or more unpaired electrons. So like something like hydrogen has an unpaired electron. So we say that that would be paramagnetic. Diamagnetic is when all the electrons are paired, so they're only slightly repelled here by the magnetic field. Essentially, magnetism dies because the electrons are paired. So that's how you remember the diamagnetic. Magnetism dies because they're all paired. If you look at helium, they're totally paired up here. And this relates to the two spins. Remember, we have plus 1/2, minus 1/2. So for the elements that are diamagnetic, all the electrons are paired up. Essentially, the two spins cancel out here. So you could see questions about this. They could ask you to look at a set of elements and say, like, which of these is the most paramagnetic, or something like that. So you do have to kind of maybe look at the orbital diagrams and see how many unpaired electrons there are for an element, but definitely know these two terms and be able to apply these terms to different elements. Another new term that we have to worry about here for AP is isoelectronic species. Basically, anytime you have two elements here that have the same electron configuration, remember this would be due to charges because electrons can be lost or gained to be like that noble gas configuration. So anytime you have two elements here that have the same electron configuration, but their radii or their sizes are different, we call them isoelectronic species. So for example here, all of these particular elements or all of these species here have the electron configuration of 1s2, 2s2, 2p6. Essentially, they all resemble neon in terms of their electron configurations. All right, neon is a noble gas, has 10 electrons, but they all aren't neon because they don't have 10 protons to be neon, but their electron configurations resemble neon. So if it was fluorine 1 minus, it would gain 1 electron and it would resemble neon here in terms of 1s2, 2s2, 2p6. Same thing for oxygen. He could gain 2 electrons, be the same configuration. Sodium, on the other hand, could lose 1 to be like neon. Magnesium could lose 2 to be like neon. But the difference here is, obviously, they would not have the same number of protons, and their sizes would be different as well. Okay, so if you remember here, greater nuclear charge, the smaller the atom will be. So when the nuclear charge is greater here, the atom itself is going to be smaller. So isoelectronic species are when you have elements here with the same electron configuration, but they're obviously not the same element because they have different sizes and obviously different number of protons as well. The last thing I want to point out in this video, obviously you are responsible for doing all the different electron configurations, being able to determine valence electrons, and so on. I just wanted to point out one other difference here, okay? So you might need to go back and review, if you need to, how to do SPDF or kernel notation. But if you remember, we did talk about exceptions in honors here. Chromium and copper, they move 1 electron here. So for example, if you see here, chromium would not be 4s2, 3d4. Chromium is actually 4s1, 3d5. he moves one electron into the d sublevel so that each orbital has one electron in it. And we said in honors that this was due to stability. Copper and chromium did this due to stability. Well, that's not entirely true. It's definitely not an AP level explanation. And there's actually a little bit more going on here. But the easiest way to explain this is that these exceptions happen because there's less electron-electron repulsions. It does tie in with energy differences as well, but as long as you realize you can't just say these differences happen because of stability, you have to understand that there's more going on. There's less electron-electron repulsions taking place, and that's why these electrons are moved for copper and chromium. All right, so just be careful with that and realize here you are responsible for the other forms of electron configuration that we did cover in honors. I tried to focus on this in this video, some of the newer stuff that we didn't necessarily see in previous courses.